Yeah, we're ready when you guys are.
Hello guys, our project is the Kaggle competition. And in our team there are Luke, Friday, Jose, and Rajesh, and me. And then here is the content of today's presentation. First, we're gonna describe this competition and then introduce some features, and then the EDA part, imputation engineering, and so on. So the project is the fraud detection competition on Kaggle. And then the data set, we got 4 data sets in total, each in the identity and the transaction. Like for identity, we got the train data set and test data set, and then for transaction, we got 2 data sets. So it's 4 in total. And then we could combine the data set by the transaction ID. So after the combination, after merge all the data set, for the train data set, we got 5,900 observations, and then there are about 3.5% of fraud, so it's quite imbalanced data. And then here are some features, like transaction DT is the time delta, and then we got the transaction amount. And for the card 1 to 6 is the payment information, is credit card or debit card, and the information of the company, is Master, Visa, or something like that. For the address is the billing address, and then for the distance is the distance between the billing address and the mailing address. And then we got the email domain is just the email domain, and then for the C, the real meaning is must, so we don't know what is the real meaning is. And for D to D15 is the same, that's the time. And for M, we got M, that's the categorical, and that's the such as names matched on cards and address. And we got a lot of V features. It's more than these hundreds of V features. Okay, so the problem here is for the most of the features, we don't know the real meaning.
Okay, so for doing exploratory data analysis, one of the first things that we found is the data set is very, very sparse. Only a little bit right below 3.5% of the total transactions were fraud, so it's either 1 or 0 if it's fraud or not. So you can see right there that it's heavily skewed towards not being fraud, which made it a lot harder to predict off of. And one of the other things that we found immediately was how imbalanced the data set was. You can see here, this basically shows you how imbalanced it was. There's train on the left and test on the right. And one of the things that we found is that train was collected before test. Another thing was that transaction DT is a time delta gap, not a timestamp. At first we thought it was a timestamp because DT, date time, that's what we thought. But it's actually from a date whenever data was first started getting collected, and then it's basically just like a time delta from that first date. Every single observation after that is the gap between it. And this is to help visualize that. So we have partitioned it on sequence and then day. It's basically a lot of noise, but we were just trying to visualize that you can understand it's a time delta gap and not an actual timestamp. And then below we did a time sequence and week. And then so it's for the most part noise, but basically we just wanted to help people visualize that you're looking at a time delta gap. And then the next one is more of the same. We just did it by weekday, hour, day, and then the year of the month. And so there is some variability. Obviously, certain times have more fraud than others. But the main point is that we're just trying to show that it's a time delta, not a time stamp. We thought that was important because it gives a lot more context to the data. Considering a lot of it is anonymized or masked data, a lot of the ID things we weren't actually allowed to understand what they are because they have to hide their clients' data. And so we thought this was one of the more helpful things that we could understand right off the bat. And then these were just some other interesting things we found when we were doing exploratory data analysis. We found that when people try to hide their IP, they make their IP proxy anonymous. There's more fraud. I guess that kind of makes sense because if you're trying to do fraud, you want to hide your IP proxy. And then another one was there was a lot more fraud on mobile as a percentage of the data than there was on desktop or anything else like that. I guess that makes sense as well, because when you're trying to hide what you're trying to do when you're committing fraud.
All right, guys, I'm gonna walk you through the missingness and imputation part. I personally find. Wow. Sorry for that. I personally found this data set is extremely hard. One of the reasons that it's hard is because it's all anonymized, the data, so that we almost don't know like the 90% of the columns meaning, so that we need to guess and to do some data mining and to do some like inference to guess what are the meaning of those missingness. All right. So this data set has very high percentage of missing values, especially the weak columns that we can see from here, which are more than 90%. And for dealing with this missingness, we check about the distribution of those columns further, and we found the distributions weren't normal as well. Thus, our strategy of imputing those missingness are originally we planned to drop all the columns with over 80% of missing value and impute those columns with less than 20% by the mean of each row's product CD, and use the machine learning model with the columns without missing values as input variables to predict the remaining missing values. This method is quite precise, but also very time consuming. Considering to the time limitation, we decided to take the plan B. And the plan A is also hard to impute because of the anomalized data. For plan B, we took the advice from our mentor, who is Bernard, that can last a week, so that we impute all the missing values with -999 first, which is very fast. And the model can still find some pattern inside of our data set instead of losing all the information if we drop them. And we can do more complex imputation methods afterwards, like the plan A, if we have extra time. So that's also one part of our future works.
Okay. So as you saw, given the sparsity of our data and because it was so anonymized, our best way to combat that was to do extensive feature engineering. So our plan of attack was to first deal with the non-anonymized columns first, and from there deal with the anonymized afterwards. So for instance, as you can see on this graph, we created a days feature out of the transaction time delta. And as you can see, there's patterns that for each week, that the first day of the week, although that's still anonymized, is typically lower than all other days. And there's always a peak at the end of the week, which kind of makes sense if you think about it in terms of weeks. Sundays, or you would assume that maybe Sundays wouldn't have as much transactions as Friday nights or Saturdays nights. And so we did extensive feature engineering on the times. We divided it into rush hours, sleeping time, partying hours, and try to find certain trends in that to help inform our model. We also so this is per day the amount of the count of the amount of transactions. We also another of the features that we that was not anonymized was the emails associated with the transactions, and we divided between whether they were foreign or domestic to see if there were any trends in that. And you can go to the next slide, actually. And then so we moved on to the anonymized afterwards and feature narrated based on that. Because the V columns were engineered by the company themselves, we indexed on those the most when we started doing feature engineering. And as you saw before, that there were correlations in the missing values between the V's. So what we did is we tried to find correlations between the non-anonymized and the anonymized V columns to see if there are any trends in that. As you can see, according to the product CD and each of the V's, the anonymized V's columns, the S, which that is still anonymized, we don't know what that is, always had a considerably larger amount mean values than the other ones. W was consistently second. And so we computed by melting those V columns that had similar missingness and try to find correlations among the other values. Okay, so so given the imbalance of our data, it was important for us to first reduce the features so that when we do our balancing techniques, they're informed by the most important features. So we attempted 3 different types of dimensionality reduction. We started out with PCA. This is actually a scree plot from our first PCA that we ultimately went with. We ultimately cut it off at about, and I'm sorry it's hard to see, but about without 2% explained variance. We also did a lasso, and we also attempted to do a sparse PCA, which is a version of PCA that better handles sparse inputs by introducing an elastic net or a lasso feature to help explain the linear relationship within the PCA. However, we didn't ultimately go with that because our understanding of it wasn't as much as we understood regular PCA and lasso. And yeah.
Okay, so as we have earlier mentioned that we really have a lot of imbalance in our data. So we overcame that with 2 sampling techniques. One is the oversampling and the other one is through SMOTE. Basically, the reason behind using oversampling technique is all we have is 500,000 rows. So if we are using undersampling technique, that is when we are losing a lot of information. So we picked up oversampling technique. So oversampling technique is nothing but just improvising the minority with just to balance the data. And the next one, which is more hybrid, which is having more hybrid technique, is SMOTE. This is nothing but synthetic minority oversampling, which internally uses the k nearest neighbor from one of the randomly selected point, and it will fill the data accordingly. So after using this mode, we were able to oversample our data, which is around 3.5% to equal ratio of being fraud and not being fraud. These are the balancing techniques, 2 balancing techniques which we are able to use. And moving on to further, the modeling. So basically we tried to perform a model before doing before using imbalancing techniques. So we ran XGBoost. We tried to do an imbalance internally, an XGBoost. So we use 2 techniques there. One is using the weights and XGBoost with weights, and the other one is XGBoost POS weight. So the difference between these 2 is XGBoost we are manually actually mentioning the weights where we are balancing the minority and trying to perform an algorithm. And the second one is using the POS weight, which actually uses the ratio of unbalanced weight with the balanced weight, and it performs the algorithm. But we have actually drastically failed in those models, so that's the reason we have used the earlier technique SMOTE. After using SMOTE, we just ran the XGBoost base model, and we were able to get the scores accordingly. And we also used light GBM here, and we were able to, by using light GBM, we were able to fine-tune the algorithm itself nearly 200 times, and we were able to get the best scores of 9.7 accuracy. Yeah, so speaking about the metrics which we have are accuracy, precision, recall, and AUC. So the reason is we are trying to predict the false negative. So that's the reason we have chosen those metrics. And the next is we have also chosen the ROC curve, and the reason behind using the ROC curve is while the Kaggle organizers have asked us to submit it in the form of ROC curve and accuracy, and also better to do it with the AUC, so area under curve. So that's the reason we have used ROC and AUC. Yeah. So moving on to further, future work. If we really had some good time with the data set, we tried to do some grid search and PCA for our feature engineering, which actually took 13 to 16 hours, but still we were not able to end it, so we have to interrupt it manually, and we were not able to finish it. So to utilize such kind of thing, we want to use cloud computing like AWS, and try to perform these techniques through AWS. As I mentioned, for PCA, we want to deal with also the sparsity. We want to use AWS. And if we would also be given some time, we would for sure use optimization techniques like Bayes optimization and GPY optimization, and also stratified K-fold. Yep, so these are the techniques which we would be using for our future work. That is all we have, and thanks for listening to us. So any questions? Thank you.
In terms of size, sorry.
We have around 540.
Memory size.
I'm sorry, I don't recollect anyone.
Like roughly ballpark. You said you ran into a.
Oh yeah, so it is it is 700 MB, and we reduced using the memory reduction to around like 78 or 76 MB.
I wonder what you ran, because 700 MB shouldn't be that bad.
Yeah, so that's only our test data. That's just a training data set. Yeah.
But that was a training.
Just the training data set.
So maybe I can take a look at the code sometime.
Sure.
But a few things. So when it looked like the goal of your project was to kind of try out Kaggle competition, right? So I think obviously evaluation of a discussion of how you evaluate against the leaderboard, or what were methods you understood about how to work the problem out in relation to that would be good. I know that Bernard is a big fan of tree-based models, from the if I recall correctly. So that's something to be mindful about in terms of his imputation suggestion, because you obviously throw -999 to a linear model, and it's going to completely destroy what's going on there.
So we also used actually -1.
Oh, okay, yeah. So maybe
so the results which we got are through by using -1.
Okay, all right. So yeah, that's what I was going to say, because that was a big flag that as soon as I heard it. So I think anomaly detection is obviously a very important field of data science, and also specifically for fraud detection. Be mindful of the terms you guys use, like sparsity generally relates to actually obviously the data set itself, and then what you're looking for was actually the imbalance. It's an imbalance classification task, which is
one of the most common things, of course, in real-world data science classification tasks. So when you're dealing with imbalance, I would say, A, don't worry too much about the accuracy itself. Usually for an imbalanced data set, especially if it's something like 99%, say, class one, and then say it's 1% class 2, 99% accuracy is going to be what you expect anyway, more or less, just from guessing class 1 the whole time. So what you want to consider more is, of course, detecting what's your actual accuracy in detecting the minority class, and you may want to also tune your cross function according to that. So
yeah,
for
cross-validation.
example, yeah, you can actually select. I think one of the things you can actually choose instead is to for you to be penalized by log loss instead. Okay. So log loss basically says if you're wrong with a very confident prediction, then it could go towards infinity. So you could get a huge penalty from just saying, I 100% believe this is a 1 when it should be a 0, which is what's going to happen if you blanket guess 1 on your majority class, for example. And then you'll get a great accuracy in a traditional model, but then actually if you use log loss instead as your penalty, it will actually penalize against that, and then you'll get a model that's more robust against imbalanced classes. That's just one example.
Okay.
So those things to just kind of keep in mind. It's a really interesting kind of problem and very common in the real world, but then as a result, you want to actually take that into account of how to tackle that specific imbalanced class issue. That's what I would focus on.
Okay. Okay, thank you. Anything else?
I had a question about the bar that you have shown. Could you explain that?
Which bar?
You had a bar chart where you were talking about imbalance. Yeah, what exactly are you trying to show there?
Okay, probably can you show her the first bar plot and then, where we have the data?